Today, our topic of discussion is top gas dust, and for this, we have taken a typical example of 620,000 normal cubic meter of top gas per hour generation. Out of this, 14 gram per cubic meter goes to the dust catcher, 2.1 gram to the scrubber, and zero point zero 0.05 gram recirculate into the system. And this typical breakup has taken to aware the blast furnace steam so that they aware about what sort of size distribution is occur across the system when outgoing gases enter from dust catcher to scrubber and a scrubber to finally TRT inlet end. Now let's understand what this means and how we can address it. Coming to our next slide, where it shows that top gas is generated when hot blast reacts with the coke and injectant at the temperature around 2000 to 2200 degrees centigrade. Is a short of a typical example as taken. It rises through the furnaces, heating, reducing the burden. This is basically a generic short of processes occurred in the furnace. The gas typically contain nitrogen, carbon monoxide, and carbon dioxide. Its composition is a key indicator of furnace performance. Now coming to the top gas configuration. Top gas dust consists fine particles carried out with the top gas stream. These include unburned char from injected fuel and fines from the body material like ore and coke. High dust levels signal very big inefficiencies and can lead to instability as well. Reduced efficiencies is always signifies by the more dust generation in the outgoing gases. It also helps in contributing equipment damages too, and there is a safety risk or hazards also. Now coming to the primary causes of increased dust, these are basically three main causes of increased top gas dust. One is a very obvious one, which is incomplete combustion of injected fuel. uh, Excessive fines in the burden material is also a big reason, and erratic gas flow, which is related to the process expert skills and diagnose the corrective measure, and these also related with the poor permeabilities. So let's explore each of these in a greater details. Now coming to the incomplete combustion of injected fuel, especially in the context of when pulverized coal is injected, ideally it should fully gasify, but at high injection rate, their discrepancy may occur up to 30% remains as unburnt char. So this char travels upward, increasing carbon content in dust immensely. And low volatile coal is, as we know, it is a less reactive and longer residence time owes in the its combustion also. So now coming to the excessive fines in the body material, as we have already discussed, that proper size distribution of ore, sinter, pellet, and coke is crucial. Fines block the gas flow, causing channeling and uneven temperatures. Uh, mm, uh, for reference, the permeability of 4 is taken as 1, coke is 13, but cohesive zone is zero point 0.2 to 0.25. So this shows how fines drastically reduce gas flow. So with the help of this typical example, we can sensitize the team uh, uh, about the importance of the this fines generation and further reduction in permeability. Now coming to the erratic gas flow and poor permeability, you can see that uneven gas flow allows bypassing of burning zone, picking up fines, and moisture condensation from hydrogen injection or hydrogenous fuels can agglomerate the charge, increasingly intensity. So coke replacement and high gas rates also uh, reduce the permeability, creating a channels that lower reaction efficiency. Now coming to the operational impact of increased dust, we can say that increased dust affects operations in three major ways. So what are those ways? The ways are like furnace instability and temperature fluctuation. This will inevitable reduce thermal and chemical efficiency as temperature fluctuation is there and furnace is unstable. So definitely thermal stability once not there, other consequences come across like chemical inefficiencies and equipment damage and maintenance challenges are also occurring, especially when thermal conditions fluctuate, as we must be knowing in frequent sleep and a huge gas surge gets reflected in terms of bleeder lifts and disconnection of TRT again stabilizes the TRT after reducing the blast. So this also all contributes towards the inefficiency of the process and lesser production from the furnace. Now coming to the unburned char and the fines disruption, where we can say that high PCI without oxygen management raises the top gas temperature. A coal furnace often due to poor heat transfer may require reduced blast volume to stabilize the furnace operation. Now coming to the reduced efficiency, where we can say that channeling reduces heat and mass transfer. Industrial top gas temperature ranges from 110 to 140 degree, as we all keep this norms. Keeping it above 160 prevent condensation. Blast temperature adjustments also helps, but dust complicates the optimization process. So we need to have a counterbalance of optic temperatures as discussed. Now coming to the abrasive dust wear down the component, we can say that molten ash that can form shells around the raceway causing tears and blowpipe failures. Moisture condensation further threaten the hearth refractory and overall furnace integrity. Now top gas contain a combustion of CO and S2. Dust adds to a lot of time explosion risk also, especially if air ingress occurs. Maintaining positive pressure and top ignition or during the repairs are very essential. Environmentally, unburned carbon means more raw material used and higher CO2 emission. So this is also signify the inefficiency of the system. Now coming to the highlights of the key data points, the top gas composition reflects furnace health permeability ratio, shows fines impact up to 30% car at high PCI rates, target top gas temperature above 160 degrees centigrade, oxygen enrichment boosts draft, coal ash affects the slag chemistry and fluidity. Now coming to the optimize burden distribution by use of ballast stop system for precise material placement, we have to monitor the top gas hourly and use the cross beam probes to track the radial temperatures, and this can guide us a lot on what is the profile of the gases and what sort of stability is there. Direct imaging also can reveal a gas flow pattern and helps to prevent fines accumulation. Now coming to the raw material quality control, as we can say that minimize moisture in the burden material to prevent condensation is must, and use sinter and dry quench coke, control alkali and zinc to maintain furnace stability and slag quality. So raw material is the foundation to the dust control that we have learned. Now coming to the use of oxygen arrangement to raise flame and improve combustion, ensure high combustibility of injection lances, Adjust blast temperature to balance the heat and reduce the dust. This step directly impact car formation and gas efficiency. Now coming to the maintaining the slag viscosity, our aim is to be maintain the slag viscosity by in between zero point 0.2 and zero point 0.5 PAS. The high SiO2 in coal ash reflects slag basicity and fluidity. Proper slag management prevents chilling and absorb impurities, supporting a stable furnace operation. So now coming to the our next slide, which is about a continuous monitoring and adaptation, on which we can say that monitoring the static pressure along furnace height is very important, and most resistance is in the high temperature zone. Foreman and engineers must interpret data day and adapt operation to maintain stability and prevent losses. In the conclusion, we can say that top gas dust reflects inefficiency in combustion, burden and gas flow. It affects stability, efficiency, safety and sustainability. So let's commit to a proactive monitoring, training and process optimization. By reducing dust, we boost productivity, cut cost and protect the environment.